Hello, general chemistry students. Dr. Ross here with a video of some length talking about regions of a pH curve. So this is to accompany some notes on aqueous equilibria, I guess, but it will involve some acid-base material. Okay, so I'm going to share the screen. Essentially, I'm going to be sharing some notes that I've prepared, and I will be posting for you in our LMS site. I just want to say a few words about the notes here. So I should be able to set annotation up. There we go. Okay, so hopefully you can see this. So the title here says regions of a pH curve for a weak acid strong base titration. So you can learn a lot about, you can derive some equations if you look at this titration curve, so that's what we're going to do. So here, if I make it smaller so you can see the whole thing, we have a typical titration curve. So you can see that we plot pH on the y-axis, sorry, and then volume of base added in milliliter on the x-axis. And you can see a typical profile like this. You've got an initial region I've labeled A, where it's all fresh and shiny and nothing's really happened yet, so we can think about what is actually, if we're doing a regular titration from a burette into an Erlenmeyer flask, what exactly is in the Erlenmeyer flask? That would be represented by equation A. Then equation B, you can see this is not a linear part of our graph. It seems to plateau around equation B, so that's going to be our buffer region. And then we start to asymptote through point C, so there's clearly a difference going on at point C where we reach the equivalence point of our titration. And then if we add excess base, we eventually reach point D. So this characteristic curve of a weak strong titration system clearly has these four unique zones, and we're going to look at these four zones and the equations that represent those zones. Okay, so let's have a look. So again, if you keep this titration curve in mind, we're now going to look at the initial part of this graph, part A. So you can see here I've written an equation, a general acid equation, HA aqueous plus water liquid in equilibrium to give the hydronium ion and the conjugate base. Remember we said a priori that this is a weak acid strong base system. So we know that HA is a weak acid. So I've remarked here, even after equilibrium is established, the concentration of the weak acid at time t is approximately the concentration of the weak acid at time 0. So what that means is because it's a weak acid, its acid dissociation constant is a lot less than 1. So its equilibrium is still shifted left. Even when it dissociates, it only partially dissociates. So you can imagine that its shift towards the right is so negligible, we can imagine it doesn't really shift at all. Even though it does, we can conclude that it doesn't shift that much. So after it's done shifting at time t, it's still pretty much in the same place as it was initially at time 0. So if we look at the acid dissociation constant, we can assume, because this is a 1-to-1 ratio between hydronium and A-, the conjugate base, because they're the same concentration, we can just say it's the same as the hydronium squared, because A would have the same concentration as hydronium. So we just say hydronium squared divided by HA at time 0, Remember that we ignore water liquid because it's in the liquid state and it's a constant, so we ignore it in dynamic equilibrium. So we have our expression for acid dissociation here. If we now solve for hydronium, we effectively multiply both sides by HA at time 0, and then we square root both sides to get just one hydronium rather than hydronium squared. So we have this square root order here. We know from one of our basic log rules, and we use in base 10 because of the definition of acids and bases here. If you take log of some constant square rooted, essentially you can rewrite it, the exponent here, a half, you can write as a coefficient. So again, that exponent a half, you can just write as a coefficient a half. So that's one of our log rules. So we can rewrite this. So we take our original hydronium here, and we want to take log base 10. So we take log base 10 of both sides, and we have this coefficient a half come down. And again, we have it for this product here. We have a product, don't we? A product of K and HA. So we have the coefficient applied to both the Ka and the HA. And remember a different log rule, that when we take the log of a product, we add the logs. But because we're interested in the negative log, the sum of these logs becomes a negative because we're adding a negative log. So that's where this negative sign comes from. So here, again, if you're looking at this video, we've got the sum of terms. It becomes negative because we're interested in the negative log. And this square root exponent a half here becomes a coefficient because of our log rule here. So essentially what we have by definition, negative log base 10 is P, as in pH. So we have pH on the left of the equality here, and then we have pKa divided by 2, and then we have just this expression written here. So this is our pH equation that's happening at part A, and that governs this part of our equation here, initially in our titration. By the time we've looked at all 4 equations, we'll summarize them and look for similarities and differences, but we'll do that at the end of the video. Okay, moving on to part B. This is the buffer region of our curve, and we know that that is the Henderson-Hasselbalch region of our titration curve. So you won't be shocked to learn that we're going to produce the Henderson-Hasselbalch equation here. We have a generic equation for an acid dissociating in water to give hydronium and conjugate base. Again, we write the acid dissociation expression. So we have hydronium and the conjugate base divided by the original Brensted acid. As a denominator here, we ignore water because it's a liquid and it doesn't partake in dynamic equilibrium. We again solve for hydronium because we eventually want to get the pH. So we solve for hydronium, and you can see that we just multiply both sides by HA, divide both sides by A minus. And then we're going to do a similar trick to equation A. We're going to multiply through, we're going to take the negative log to base 10 of everything so that we can eventually convert to pH. So if we take this expression here and we take the negative log base 10, that just is written in front of the hydronium. Again, we've got a product of terms here. We've got the Ka, and then we've got the fraction HA over A minus. So we take the log of a product, we add log terms, but because we're taking the negative log, we add a negative value, so it becomes a subtraction. So that's straightforward. Then we can relabel everywhere that we have negative log base 10, we can replace that with a P. So again, we have pH on the left of the equality here. Again, pKa on the right, and then we have another expression with ratios of acid and base. For historical reasons, there's really no need to do this, but historically it's presented this way in most textbooks. We're going to use another log rule, which says that if you take the log of an expression, if you take the log of the inverse expression, you change the sign of the log. So for example, positive log a half, change the sign, becomes negative log 2/1. And we're going to do that just to make this a positive log base 10 rather than a negative, again, just for presentation effects. So if we make this negative log base 10 positive, we have to take the inverse of this log fraction argument. So we invert HA over A to make A over HA. And this is typically the way the Henderson-Hasselbalch expression is presented in a textbook, although there's really no need. But I guess historically that's how it's presented. So that's our equation B. And again, we'll compare these 4 equations at the end of our video. Moving on to the equivalence point of our titration curve, part C, or zone C. Well, at this point, the neutralization reaction of our acid and our base is done. So we just have excess conjugate base left over in water, so it makes sense to look at that. The acid and base have annihilated each other chemically, and we've got just hydrolysis products left over. So here we've got conjugate base left over in water. The conjugate base in water can hydrolyze to give hydroxide, and it can regenerate the weak acid again. Now, obviously, if we look at our expression here, the argument is the conjugate base, or at least the conjugate base of our initial expression. The way it's drawn here, it's the Brensted-Lowry base, because we've written it on the left of the equation. So it makes sense not to look at the acid dissociation expression, but the base dissociation expression. So we write Kb here. We do a similar calculation that we did in equation A, where we know that we have a 1-to-1 ratio of hydroxide ion to Brensted-Lowry acid here. So we can take the concentration of hydroxide squared. So rather than write OH minus and HA, we just write OH minus squared because HA has the same concentration as OH minus. So we've written a base dissociation constant. There you go. Couldn't think of what I was looking at. Base dissociation expression. And now we solve for OH minus. So we do that by isolating OH minus squared and then taking the square root of both sides. Again, we've got this product here. We have an exponent. We're going to take negative logs of both sides to bring that exponent down. We take negative log base 10 of both sides. Again, we've got a product. So we take the sum. When we log a product, we take the sum of the logs. But because we're interested in a negative log, it becomes a negative. It becomes a subtraction because we're adding a negative value. So it looks like a subtraction. Again, the exponent becomes a coefficient. So that's where the 2 in the denominator position comes from. So we get an expression for POH. So this is analogous to the expression we had in part A, but now we've got POH. We want to convert that to pH. So we have to use some relationships we've seen in previous chapters. So we know that the product of the acid dissociation and the base dissociation constants are the autoionization constant of water. Or if we take the P expression of both sides, again, we can make Kw pKw. But if we P this product here, we take the sum of the logs. So that's why we have pKa plus pKb. And then if I want to isolate pKb, I just subtract pKa from both sides of the expression and I get this one here. So what I'm going to do, I'm going to take my expression here with pKb and I'm going to substitute in pKw minus pKa into it. So I have POH, and then I look at my term here, pKb over 2. Well, that just becomes pKw minus pKa divided by 2. So that's where you see this expression here. And then I've got the original part of my term here, the minus log base 10, a minus over 2. So pause the video, have a look at that. You can see that all we've done, we've subbed in this expression here for pKb into this expression for pKb here. And then we're going to further sub in. So recall from our initial work up here that we said that pKw is the sum of pH and POH. So where we have pKw divided by 2, we can now sub in our expression here. For pH is pKw minus POH. So we get pH, we get pKw, and then minus POH. So we've got all of this stuff as POH. So it might be a time to actually write on this because we're getting a lot of stuff. Okay, so I want pH, and I know that I've got all of this expression for POH. So I'm essentially going to sub this in here. And then I can solve for pH. So pH is pKw minus the POH. But I don't have minus POH, I know positive POH. So I've got to take this negative sign and apply it to every single term here. So so I've got to make this minus pKw over 2. That's where this negative comes from. The minus hits that minus and makes this positive. So plus pKa over 2. And then again, the minus hits that minus and makes it positive. And then I've got this final term. So take a look at those signs. Again, it's because of this minus POH that affects all these signs in the positive POH. Okay, so then I have this expression here, and then I can start to combine terms. So I have pKw minus a half pKw. Well, that just leaves me with a half pKw. Then I have the pKa over 2, and then the final term. Okay, so that's my equation C at the equivalence point. And then finally, our final expression. So pH is now determined by the excess base acid. Remember where we are in our profile curve. So we're done with the equivalence point now. We just add an excess base if we were trying to get the profile point, so we can help make sure we know exactly where the equivalence point was by going past the equivalence point. So the pH is now just determined by the excess base added. So we've just got a bucket full of water here with excess base in it. So let's look at the autoionization of water. 2 lots of water dissociate to give hydronium and hydroxide. We've got the autoionization constant of water, which is the product of hydronium and hydroxide. We solve for hydronium, we get Kw over OH minus. We take negative log base 10 throughout so that we can eventually solve for pH. So we get negative log base 10 hydronium. Here we've got a fraction. So remember, when we take the log of a fraction, we take the difference of the logs. So we applied the negative log base 10 to the numerator, but then we subtract negative log base 10 of the denominator. The two negatives combine to make a positive. So we have this positive here, log base 10 of hydroxide. And then we just relabel anything that's negative log base 10 as P. So negative log base 10 hydronium just becomes pH. Negative log base 10 Kw becomes pKw. And then we just leave our log base 10 OH as log base 10 OH. So that's our final equation for part D. Now let's summarize our 4 equations. And let's see if they make sense. So we followed the basic math. Let's see if we have a gut feeling for what we have. So I've written the 4 equations here, and I've written them in a way that we can compare and contrast them. Okay, so if you look at equation A, I've noticed that these equations all have a water term where it's just associated with the symbol W, an acid term where we have the symbol A, and then an acid or a base term where we have either HA or A minus. Okay, so in region A, equation A, at the beginning of our titration, we have no water term. But we do have an acid term indicated by the Ka. The fact that there's a factor of 2 there, I'm not really bothered about, but we have an acid term. And we also have this acid-base term here that is common to the other equations. So does that make sense? Well, it kind of makes sense with hindsight that there's no water, because water is a product after the equivalence point. So we wouldn't expect to see water until the equivalence point, right? Because remember our definition of a neutralization reaction, acid plus base gives us salt and water. We're nowhere near that phase yet. We're still at the beginning of the titration. So it kind of makes sense with hindsight that there's no water term. We are in a beaker, in an Erlenmeyer flask full of acid though, so it totally makes sense that we have acid terms. We've essentially added no base because we're right at the beginning of our titration. We haven't really added any base yet. So it makes sense that we are dominated by acid terms exclusively. Okay, so that kind of makes sense. Equation B, the Henderson-Hasselbalch equation. Again, we're not at the equivalence point, so it makes sense there's no water. We are early on in the titration where we're dominated by acid, but we're starting to have this battle between base and acid take place. The base is being added, the buffer is resisting that addition of base as a chemical stress on the system at equilibrium. So you can see the base here, A minus, start to appear, but we've got a good domination by acid terms. So that kind of makes sense if you think about it based on where we are in the profile. Then at region C, we have the equivalence point. Now, again, acid, base, salt, water, it makes sense now that we see the appearance of a water term. Again, the factor of 2 is irrelevant. We see a water term for the first time. Does it make sense that we see acid and base? Yeah, I think it's reasonable. You know, we're at the equivalence point where, you know, the acid has mixed with the base to give water and a salt. So I don't think there's anything too suspicious about seeing water, acid, and base present in this equation because they're all players at or around the equivalence point. And then finally at part D, where we've superseded the equivalence point, we're now, you know, the chemical equation is finished, and now we're just kind of drowning the thing in base. So we kind of just have a beaker of water. We've diluted, all the acid and base is gone really. We just have excess base that we've added because we've just added so much base for some reason right at the end. So we've just got base in water and we've totally annihilated the acid at this point. So that kind of makes sense too. So I think it's useful after concluding, looking at these equations, that you look at what you have, you can compare and contrast them, and they kind of make sense based on where they feature in the titration profile. So I would encourage you to look at the video, again, have these equations next to the profile, which remember is this, and convince yourself that that's where they belong. Okay, and that will conclude this video.